Hello, I'm Fatemeh Bagheri. I'm a PhD student and working on energy dissipation during geomagnetic storms under supervision of Dr. Lopez. Here, my study is about the correlation between solar wind density and ionospheric electrojets during the main phase of the magnetic storms. So first, I'm talking about what is storms and giving you an introduction for our work. Lopez et al. In 2010 argued that the role of the density during events strongly driven by large southward IMF can be understood by considering the steady-state momentum equation, which is equation 1 in the introduction box. The balance between these two forces, J cross P and minus grad P, explain the divergence of the magnetosphere flow, which regulates the geoeffective lengths in the solar wind and the rate of energy transfer to the system. The main point is that when IMF is large and Mach number is low, the J cross P term dominates the right-hand side of the momentum equation. Increasing the IMF under this condition increases the J cross P term and then the divergence of the flow, so reducing the geoeffective lengths in the solar wind. Consequently, less flow can reach the merging line, leading to saturation of the ionospheric potential, which means potential becomes independent of the IMF magnitude. In this saturation regime, the energy transfer is controlled by the density of the solar wind, since the divergence of the flow would be inversely proportional to the flow density. Here we found two events as the observational evidences for the physical reasoning that I just explained. The first event happened on October 3, 2001. We selected the period between red lines as it showed in the figure 4 to calculate the correlation between SME index and the solar wind density. As it's seen in this figure 4, during this period, BZ and the other solar wind parameters are all steady except density. And you can see that Mach number is less than 4, which is categorized as a low Mach number event. As it illustrated in figure 3 top, the greatest correlation, which is 0.81, happens when the lag time between solar wind density data and SME index is about 13 minutes. Considering this lag time in figure 3 bottom, the red line is the best linear fit for SME and solar wind density. We repeated this procedure using the SWMF simulation for this event. We calculated the correlation between solar wind density and simulated Joule heating. Figure 5 top represents the correlation coefficient between Joule heating and solar wind density. The greatest correlation coefficient is about 0.67. In the figure 5 bottom, the linear relationship between the Joule heating and solar wind density is illustrated, which is very consistent with the observational data that we have. Now let's check another event which meets the most criteria but none of them, and see what happened during this storm. On December 20th, 2015, a double geomagnetic storms happened. The period between 610 to 810 UT to calculate the correlation between SME index and the solar wind density. As it's seen in the figure 6, during this period, BZ has a large value and is roughly constant. VBS and total magnitude of P are steady as well, but Mach number has a large value 6. And it is mostly constant, which is categorized this event has a high Mach number, not low. Thus, this value of Mach number indicated that we are not in the saturation regime. The SME index was not correlated with the solar wind density, as it can be seen in figure 7. Since the saturation of the potential did not happen, the merging interaction has a significant role to control energy transfer into the ionosphere. We found more events like the event of the June 1st and January 10. Considering all the events in figure 8, we present a correlation coefficient between the solar wind density and SME index as a function of the average value of Mach number during the selected period for each event. As can be seen, the correlation coefficient gets larger as the Mach number decreases, indicating that the effect of the density is greater. But why this happened? Because a lower Mach number leads to a more saturated ionospheric potential. Therefore, the intensity of the auroral electrojet mostly depends on the solar wind density rather than the other parameters of the solar wind. This means the variation in the SME index are more correlated to the variation of the solar wind density. So here is our study conclusion.